The probability of an event is a way to quantify our uncertainty about whether or not the event occurs. For example, we might say the probability a coin lands heads is 1/2. But what if we see a person flipping a coin 10 times and having it land tails every time? There are two types of people. I was told once that the probability the coin lands heads is 1/2, and my mind will never be changed under any circumstances, regardless of facts, evidence, sworn affidavits, criminal convictions, or anything else. Nope, never going to change my mind. And then there are the people who think, maybe evidence should change my worldview. So we can distinguish between two things: the probability of an event A, which we write this way, and the probability of an event A given that we know a second event B has occurred. We write this way and call this the conditional probability of A given B. We'll refer to A as the event of interest and B as the conditioning event. Now, without knowing the exact probabilities, we might still be able to decide how we'll adjust a probability in light of additional information. For example, the probability a flight is delayed by a snowstorm is some amount which we don't know, but the probability a flight is delayed by a snowstorm, given that the flight is in June, which we'll write this way, we don't know that either. But our experience with the real universe suggests that because the flight is in June, the probability it will be delayed by a snowstorm should probably be a little less. Now, conditional probability is very tricky because we speak in English, or Dutch, or Urdu, or Wenami, or any other natural language. Math is straightforward, but translating from a natural language to mathematics is hard. We often embed the conditioning event without even using giveaway phrases like given that. The important distinction: if you know with absolute certainty something about the situation, you are dealing with a conditional probability. For example, the probability a June flight is delayed by a snowstorm. In the statement, we are given one fact about the flight: it is in June. On the other hand, the probability a flight is in June and delayed by a snowstorm, we don't know the flight is in June. That's part of the probability we're trying to find, and we don't know that it was delayed by a snowstorm, so this is not a conditional probability. Or let's take another example. Let D be the event that a flight is delayed by a snowstorm and J the event that it is in June. To express the probability that a June flight is delayed by a snowstorm, we know the flight is in June, so the conditioning event is J. What we don't know is whether or not the flight is delayed, so that's the event of interest, and so this would be the probability of D given J. Or the probability a flight delayed by a snowstorm is in June. So here we know the flight has been delayed, so that's the conditioning event. What we don't know is when the flight was, so that's the event of interest, and so this would be the probability of J given D. And finally, the probability of a June flight delayed by a snowstorm, we don't know when the flight was. And we don't know if the flight was delayed, and since we know nothing about the flight, this is not a conditional probability. We want the probability of a flight being delayed and also in June, and so that's the probability of a conjunction. And here's an example of just how difficult it can be to identify conditional probabilities in a natural language. These two statements appear to be almost identical. A single word changes this conditional probability into an unconditional probability. Again, this could be even trickier because conjunctions are often stated without using and. For example, suppose a store sells A-line dresses in various colors and materials. Let A be the event that the store sells an A-line dress, B the event that the store sells a blue dress, and C the event that the store sells a dress made of cotton. The probability a store sells a blue A-line dress, so we know nothing about the dress that's sold, So this is an unconditioned probability that the dress is both an A-line and also blue. The probability a blue dress sold by the store is an A-line dress. Here we know the dress is blue, so this is a conditional probability where we know the event B has occurred, so this would be the probability of A given B. The probability an A-line dress sold by the store is blue. Here we know the dress is A-line, so the event A has occurred, and so this is the probability of B given A.